In this problem, I'm going to sketch a velocity graph and an acceleration graph given a position versus time graph and the associated function that goes along with that. In order to find a velocity function, we need to take the time derivative of the position function. So I'm going to do that. I'm going to find d over dt of the function 1/8 t cubed minus 9/8 t squared plus 15/8 t plus 41/8. All right, first of all, I'll use the power rule for differentiation, and we'll get 3/8 t squared for that first term. We'll have negative 18/8 t plus 15/8, and that will be our velocity function. All right, next thing I want to do is I will want to sketch it. And I can use some facts from the graph that I see in order to help me sketch it. For example, like let's just look at some features here of the graph. Here, notice there's a local min. Now, one thing about local min is that it is a place where the velocity needs to be 0. So when I go down here to sketch my velocity function, I'm going to make sure that I have a 0 on that graph where the local min happens. Now where else would the velocity be 0? Oh, right here. There's a local max there. So we want the velocity to be 0 there too. Now what other features will be important? Well, I see that there's a point of inflection here. So what will happen at that point on our velocity graph? Like we know, for example, that if you trace these mins and maxes down, that those are going to be points where our velocity has a 0. But what will happen if we trace the point of inflection down? Well, we'll see that the velocity will have a min or a max there. So since that's such an important point, let's go ahead and calculate using a table here what the value of it would be. So in the table, you pick certain times that are important, and then you plug that into the v of t formula to see what the velocities are at those times. I might try a time of 0. I think that's going to be important. I'll also use a time of 1, and a time of 3, and a time of 5. That should help me sketch it pretty well. So when I plug in a t of 0, we're going to get the constant 15/8. Now on calculator, that comes out to a 1.875 as a decimal. Let's just plot that point right now. Okay. Now let's plug in a 3. So we're going to need 3/8 times 3 squared minus 18/8 times 3 plus 15/8. On my calculator, I get negative 3/2, which is negative 1.5. Let's plot that point. Okay. I think that we have more than enough points now to complete the curve. And so let's go ahead and draw that. Okay, nice. That's our velocity function. What I'll do next is I will take it even farther and find the second derivative. That's going to be the acceleration. So one way of writing that is that the acceleration is the second derivative of the position function. But since I had just calculated the first derivative of that position function, I'm going to use this definition of acceleration. It is going to be the derivative of the velocity with respect to time. So all I need to do here is I'll take the derivative of the formula above, 3/8 t squared minus 18/8 t plus 15/8. So we're going to get 6/8 t minus 18/8. It's going to be linear. And we could even reduce that to 3/4 t minus 9/4. Alright, so what does our original graph tell us about the look of the acceleration? Well, points of inflection turn out to be useful because they are points where our second derivative is going to be 0. So when I go down here and just trace that important x down, I need a 0 right here. Now, what else will happen? We need a intercept of negative 9/4, and according to calculator, that is negative 2.25. And that's all I really need to sketch the curvature of the acceleration. I can see that it is linear, and it's going to look like that. Okay, great.